Okay, let's get back to Module 3, Part 3. Let's do some applications of the mean, variance, and standard deviation. Now that we know how to calculate those things, what can we do with them? What do they tell us? We're going to look at a few things here. We're going to talk about z-scores, an interesting theorem called Chebyshev's theorem, the empirical rule, and we'll show you how z-scores can be used to detect outliers in your data. Let's start with z-scores. A z-score simply takes any value in your data set, subtracts the mean from it, and divides by the standard deviation. And that's called the z-score for that value. You can do z-scores for either a sample or a population. For a sample, the sample mean, remember, is x bar, and the sample standard deviation is s. So for any value in your sample data, let's call it xi for the ith value, you simply subtract the mean, divide by the standard deviation to get the z-score for that value. Similarly for a population, the mean is mu, the standard deviation is sigma, xi minus mu over sigma gives you the z-score. Z-scores are sometimes called standardized values, and if you think about this formula, all that a z-score is doing is it's counting how many standard deviations from the mean a particular value is. And we'll see that a little bit more in just a moment. Note that z-scores can be either positive or negative. A positive z-score occurs when a value is greater than the mean, and a negative z-score occurs when the value is less than the mean. A data point exactly equal to its mean will have a z-score of 0. Let's do a little example. Let's treat a population of exams, let's say, that has a mean score of 70 and a standard deviation of 5. Joe scored 80 on his exam. What's his z-score? You simply take his value as your x value, 80, subtract the population mean of 70, divide by the standard deviation of 5. 10 over 5 is 2. Why is it 2? Because the value 80 is exactly 2 standard deviations bigger than the mean value. Since the standard deviation was 5, 2 times 5 is 10. 10 added 70 would give you 80. So Joe's score of 80 is 2 standard deviations higher than the mean. Here's a little chart also kind of explaining it to you using the same illustration. We have a population mean of 70, standard deviation of 5. So we've got an x variable, grades on the test, with a mean of 70, standard deviation of 5. In a sense, what the z-value does is a z-value simply is going to convert this axis. It's going to do a transformation. We're going to take x and convert it to z by taking any number x, subtracting the mean, and dividing by the standard deviation. So for example, a value like 75. If you calculated z-value, take 75 minus 70 over 5. That's 5 over 5, or 1. Why 1? Because 75 is exactly 1 standard deviation bigger than the mean. 80 is exactly 2 standard deviations bigger than the mean, so its z-value will be 2. 65 would correspond to a z-value of negative 1, because 65 is exactly 1 standard deviation below the mean. 60 would correspond to negative 2, because it's 2 standard deviations below the mean, and so on. And we'll have some uses for z-value later in this module and also later in the course. Okay, the next thing we want to look at, in fact, we'll actually use z-values in this theorem, is something called Chebyshev's theorem, which is kind of an interesting theorem concerning the fraction of data that has to be within a certain number of standard deviations of the mean. A couple of different ways to word Chebyshev's theorem. First, I say the following: at least 1 minus 1 over z squared of the items in any data set will be within z standard deviations of the mean for any z value bigger than 1. A different way to word that is my second statement here. The interval mu plus or minus z sigma contains at least 1 minus 1 over z squared of the items in the data set. And Chebyshev's theorem can actually be applied to both samples or populations, but we'll usually use it for populations. Now, the easiest way to understand what Chebyshev's theorem is telling us is to pick some values for z. Remember, z can be any number bigger than 1. Consider the interval mu plus or minus z sigma, and then calculate this quantity, at least 1 minus 1 over z squared. So let's do that on the next slide here. Now remember, z can be any number bigger than 1. I've chosen some whole numbers here, 2, 3, and 4, but z values do not have to be whole numbers. They can be fractional. Let's let z be 2. So I'm considering an interval mu plus or minus 2 standard deviations. Start at the mean and go up or down 2 standard deviations. Let z be 2. 2 squared is 4. 1 minus 1/4 is 3/4, or 0.75. In percentages, 75%. So what Chebyshev's theorem is saying is that at least 75% of any body of data is within 2 standard deviations of its mean. If you took the students in your room and considered their heights as a population of values, at least 75% of the students have heights that are within 2 standard deviations of the mean height in the room. Let z be 3, so we're considering the interval 3 standard deviations around the mean. 3 squared is 9, 1 minus a ninth is 8/9, or in decimals, 0.889. In percentage terms, 88.9%. So at least 88.9% of any body of data is within 3 standard deviations of the mean. Finally, go to z equal 4, and we'll have at least 93.75% of the data is within 4 standard deviations of the mean. Notice the wording at least. It could be more than these bounds. All the Chebyshev's theorem does is it puts a lower bound on the percentage of data in that interval. You could have all 100% of the data within 2 standard deviations of the mean, but you can't have less than 75%. Let's do an example or a problem with Chebyshev's theorem. Let's go back to exam scores. Let's say the mean is 70, and this time I'm going to change the standard deviation to be 6 points. First, I'm going to ask you what fraction of these exam scores are between 58 and 82, what fraction are between 61 and 79, and lastly, find an interval that contains at least 80% of the exam scores. You can probably see that part C is going to be a little bit different than the first two. But let's start with the first one, 58 to 82. What we have to do on this problem is basically figure out what the z-score is. That is, how many standard deviations above or below the mean are you going? If you take 82 and calculate its z-score, 82 minus 70 is 12, divided by 6 is 2. That is, 82 is exactly 2 standard deviations above the mean. Similarly, 58 is 2 standard deviations below the mean. 58 minus 70 over 6 is negative 2. So my z-value here is 2. I'm going mu plus or minus 2 standard deviations. And as we just learned a minute ago, when you go mu plus or minus 2 standard deviations, you have at least 75% of the data. So the answer to part A is at least 75%, because your 2 standard deviations are on the mean. Part B is very similar to part A, except we consider a different interval, 61 to 79. So let's draw that picture here. Now we want the interval from 61 to 79. Again, calculate the z-scores. For 79, you have 79 minus 70 over 6, which equals 1.5. 79 is exactly 1.5 standard deviations above the mean. Similarly, 61 is 1.5 standard deviations below the mean. So our z-value to use on part B is 1.5. Now you have to go back to the theorem, calculate 1 minus 1 over 1.5 squared. Let z be 1.5, square it, take 1 minus 1 over 1.5 squared, And you should get about 55% or so, roughly 55, 56%. So here's part B down here, at least 1 minus 1 over 1.5 squared of the data, which is about 55% or more. So at least 55% of the grades on this exam were between 61 and 79. Now part C is a little different than the first two parts. On the first two parts, I gave you the interval, and you had to figure out the fraction of scores. On part C, I give you the fraction of scores I want, and you're going to have to figure out the interval. I want the fraction to be at least 80%. To do part C, we're going to have to start off with an equation. Chebyshev's theorem tells you that at least 1 minus 1 over z squared of the data is in the interval mu plus or minus z sigma. So we want 1 minus 1 over z squared to be 0.8. Since the problem told you, find the interval that contains at least 80% of the data. Notice we have an equation with one unknown here. One equation, and the z value is the only unknown, so we have to use a little algebra to solve for z. Hopefully you remember a little bit of your algebra. This is just solving for one variable. You don't necessarily have to do it the way I did it here. I subtracted 1 from both sides, then multiplied both sides by -1 to get rid of the minus sign. I cross-multiplied, divided both sides by 0.2, which gets us down to z squared equal 5. Take the square root of both sides. This means z has to be the square root of 5, which is about 2.24. Whichever way you wanted to approach solving that equation is perfectly okay. Just work through the algebra. Now, once we have the z value, now we can finish the problem. The interval has to be mu plus or minus z sigma. We already know the mean is 70. We have the z value is 2.24. The standard deviation is 6. Calculate that out, and you'll get an interval from 56.56 to 83.44. So this is telling us that at least 80% of the scores would have to be in the interval from 56.56 to 83.44. Notice that Chebyshev's theorem gives a pretty good interpretation to the standard deviation. Remember, the standard deviation is supposed to be a measure of the spread or variability of a distribution. Well, basically, Chebyshev's theorem gives us at least a certain percentage of data that has to fall within so many standard deviations of the mean for any variable. It's one of the amazing things about Chebyshev's theorem is that it works for any set of data. Okay, next we're going to look at what's called the empirical rule. Now, one thing, let me go back for just a moment to Chebyshev's theorem. Notice there's a certain vagueness in Chebyshev's theorem at those words at least. It could be more than that. At least 75% of the data lies within 2 standard deviations of the mean. It could be 80 or 85 or 90 or all 100%. One of the reasons why there's a certain vagueness in Chebyshev's theorem is because it works for any distribution, no matter what shape the distribution has. Suppose, however, that we had a so-called normal or bell-shaped distribution, looking something like this. Now we can be more specific and more precise about the fraction of data in certain intervals. So what the empirical rule is it's an approximation. I'm actually going to give you the exact values in a minute too, but we'll see later in the course where those come from. Consider the interval mu plus or minus 1 standard deviation. That contains about 68% of the data. Mu plus or minus 2 standard deviations contains about 95%, and mu plus or minus 3 standard deviations has almost all of it, 99.7%. If you want the exact numbers, I have them here on the next slide. Start at the mean of a normal distribution. Go up or down 1 standard deviation, and you're going to have a little over 68%. It's actually 68.26%. But for right now, you can just remember the number 68% for 1 standard deviation. So from mu plus 1 standard deviation to mu minus 1 standard deviation, That interval is about 68% of the data. Go out 2 standard deviations, and you've got 95.44%. And go 3 standard deviations, and you've got 99.72%. Almost all of it. Now we actually know more than what we have there, because remember, this is a bell-shaped symmetrical distribution. So it's the same on both sides. So for example, if 68% roughly is within plus or minus 1 standard deviation, well then half that from the mean up 1 standard deviation would have to be 34%, or half of the 68. If 95% is within plus or minus 2 standard deviations, the other 5% has to be half above 2 standard deviations and half below it. And we'll see that as we do a problem in a minute. So let's do a problem. Suppose that IQ scores are normally distributed with a mean of 100 and a standard deviation of 14. What percent of people have IQs between 86 and 114? What percent of people have IQs of 128 or higher? What percent of people have IQs from 100 to 114? Let's start with the first part, 86 to 114. You might notice that that's exactly the mean plus or minus 1 standard deviation. Let's take a look at a graph here. Remember, the mean was 100, the standard deviation is 14. So going from 100 to 114 is exactly 1 standard deviation. Going from 100 down to 86 is exactly 1 standard deviation. And the empirical rule tells you that plus or minus 1 standard deviation is 68% of the data. Let's look at part B. What percentage of people have IQs of 128 or higher? Notice that 128 is 2 standard deviations from the mean. Remember, the standard deviation is 14 points. The mean is 100, so 128 is 2 standard deviations above the mean. But notice the problem asks you for 128 or higher. You put everything back here. 2 standard deviations around the mean would be from 72 to 128. That contains 95% of the data according to the empirical rule. So where's the other 5%? Half of it would have to be below 72, and half of it would have to be above 128 by symmetry. So the answer to part B is about 2.5% of the IQ scores would be above 128. And the last part of the problem, I believe, simply asked you for the interval from 100 to 114. Yes, from 100 to 114. And that one should be pretty easy because it's just going to be half of the interval that we had on part A. Part A was 86 to 114. That's the mean plus or minus 1 standard deviation. So 100 to 114 is going to be half of 68, or 34%. Again, we can see that on our graph. (100 to 114) is half of the 68% on the empirical rule, or a total of 34%. Okay, so the empirical rule and Chebyshev's theorem both give us a little bit more concrete interpretation about the mean and standard deviation, especially about the standard deviation and how it's a measure of the spread of a distribution. One other thing we can do with what we've seen here today is we can talk a little bit about detecting outliers. If you go back to Chebyshev's theorem, at least 75% of any body of data is within 2 standard deviations of the mean. By the time you get to 3 standard deviations, you have almost 89% of the data. And if you look at the empirical rule, by the time you get 3 standard deviations, you have 99.7% of the data. So what this is telling us is that most z-values, which count standard deviations from the mean, most z-values are going to probably be 3 or less in absolute value. 3 or less, or -3 to +3. So we're going to define an outlier as a z-value bigger than 3 or below -3, outside the plus or minus 3 range. Now that doesn't mean that it couldn't happen. You can get z-values of 4, 5, 6, 7, whatever, but they just become rare. A z-value of 5.2 means you're 5.2 standard deviations above the mean. That's quite rare. It happens a very, very tiny percentage of the time. One of the reasons we care about outliers is you could have an error in your data set. There are computer programs, for example, that'll take a body of data and calculate all the z-values. If you see a z-value of 5.2, something 5.2 standard deviations above the mean, you might want to check the data set and make sure that wasn't just somebody typed in a number wrong or put a number in the data set incorrectly. The number could be correct, but also remember that extreme values can distort statistical results. So if you do have one value that's 5 standard deviations from the mean, it could have some distorting effects on, we already know, for example, the mean itself is getting pulled in that direction. So just keep that in mind. Okay, that's the end of part 3 here, and in part 4 we're going to start looking at 2 variables.